Okay, so ln of n factorial, he said, was equal to n ln of n minus n. This is not an actual true equality, it's just an approximation. You said you recognize this, actually, which is nice, as the integral of ln x dx. That's cool, I'm glad you remembered that. What can you say about log of n factorial?
Well, it's just log of 1 times 2 times 3 times n. You could call it like this, and then you can split this up if you wanted to. You could say it's log 1 plus log 2 plus log 3 up to plus log n.
Okay. Which is interesting.
And this, I guess, kind of matches up.
Sorry about that. Sorry, I kicked the camera. Alright, go ahead.
This kind of matches up to this because it's kind of an approximation for an integral. You take intervals of a function and you're just summing them up.
So, what are you summing up when you take an integral?
You just, so like ln looks kind of like that. You're just taking.
So we'll draw that bigger.
Yeah, we're taking intervals and we're just summing up areas of rectangles.
Okay. Interesting. I guess I should have made those two ends match, but anyway, that was a little sloppy. So draw your picture and tell me what you're saying.
So we have ln n looking something like this, and then we've got 1. These are all linked to 1. So you can see we're just summing up rectangles, and then as ln n gets bigger, it gets more and more flat, so the rectangles are going to be a better and better approximation for how it actually looks.
Okay.
So as we get bigger and bigger, this is a better and better approximation for this.
Okay, yeah, that's actually a very good, very nice hand-waving explanation. So let's I'll just try to replicate your drawing here really quick. So if we do this Riemann sum with length of 1, each of these has length 1, and the height is ln, in this case would be 1, 2, 3, 4, 5, 6, ln 6. We know that ln gets flat. In fact, the derivative of ln is
1 over n.
1 over n. So it's getting very flat as n gets large. So these rectangles become pretty good approximations for it. And so whatever we want to call the area here, if we want to do the integral from 1 to n or 0 to n, I guess it doesn't really matter. We get this n ln n minus n term from one of the endpoints. And we get a decent approximation. Well, maybe anyway. Like we have these error terms, and hopefully they don't add up to be something that's too large.
I mean, the error terms are going to get smaller and smaller as n gets bigger and bigger, and ln of like 1,000 shouldn't have the 1,000th rectangle shouldn't have a large error term at all.
Yeah, it shouldn't. But the problem is they're cumulative. They're adding up. So we hope that they're not getting too large. But we're going to check right now on Mathematica how large they get, just to check.